how's it going? There we go. Hope y'all are doing alright today. I have to say, I really enjoyed a Monday morning where I could sleep in a little bit since everyone was taking a test on Monday. Of course, it made it today that much more difficult to wake up for it. But, it was nice on Monday. So, and from what I can tell, most of you decided the same thing too, which is fine. I understand that. All right. There we go. Okay. Hopefully I'll get the test graded this week. If not this week, then if not this week, then the weekend. So we'll have it by Monday, for sure. But I hope to do it like tomorrow night or something. At least partially, but we'll see how it goes. Okay. Anyway, glad y'all got through the test okay. Hopefully it went well. Some of you voiced some concerns about you think or you entered the answer correctly and it counted incorrect. I'll go back and look at it because it could be. If you have an extra space in there, it's just for whatever reason it doesn't like to count those. Anyway, I'll look at it as I go through and grade, and I'll give back points where you deserve them. So. Yeah, I saw that problem. Yeah. Okay, there we go. All right. Today we're going to start chapter 6. Now, essentially, we have 5 sections left to cover, for all intents and purposes. We have 4 class days to do it. And it would be great to review for the final at some point. Probably what I'm going to do, and I'd hate to do this, but I'll probably schedule a final review outside of normal class time. But then at least the video will be available for everyone if you can't make it to the review. And I'm thinking, and this is like 2 weeks from today, or, well, actually 2 weeks from tomorrow, at like on a Thursday at 1 in the afternoon, which is normally when I finish teaching on Thursday. I just have office hours during that time. So I will certainly talk about that again after Thanksgiving. So I think there's too much we need to cover prior to that. I just need one extra day. And it's like that in all my classes. Actually, my calculus class is doing okay. Um, well, for a different reason. But I managed to cut some things out of there. But I can't really cut anything else out of this class that I haven't already. So, just in the interest of being ready for the final exam. So, it'll still be on Twitch, so you'll still be able to watch it if you don't watch it live. Exactly. And that's my intent. So, yeah. Yeah, crazy time right now, and then we have all the holidays coming up, and then just hope your family's not passing it around, the virus. All right. Um, I don't know. Uh, I did ask y'all to go fill out that short form when I made that announcement. I guess it was last week. Um, and I'm not sure if everyone's going to take it in person or online. Or if you've chosen online, you'll take it online. If you've chosen in person, you take it in person. I'm not sure how it's going to work. But as soon as I know, I'll relay that information. I think online's a little bit easier, and in this case, a little bit safer. Um, but we are required to have a proctored final. So unless you have a camera, then that makes proctoring it difficult if you don't have that. So like a webcam, or I'm not even sure what else they're talking about. So. Well, what it does is we subscribe to a proctoring service, and we actually made. What we may do is have you connect, like on Zoom, to one of our tutors who will just keep an eye on, like 4 people taking a test, and the goal is that you will be essentially supervised digitally while you take the exam online, so they just see that you're not using notes, or I don't know what the deal is. Yeah, lockdown browser. Yeah. Yeah, that's another option. Um, I believe some of the options cost money though, and we don't really want y'all to have to spend money to take an exam. It's already bad enough to take the exam itself. Just ask you to spend money on top of it. So anyway. Anyway, I'll get that figured out and let y'all know. Um, but part of it was we wanted everyone to they could fill out that form. I don't know if you still can or not. I imagine we can, but yeah. Yeah, it's still. This is what, well, since March, basically mid March, since spring break, I've decided I would much rather be back teaching in the classroom, but not not if it's unsafe. But I'm really hoping, either one, we get a vaccine soon, which in a couple of months I think that'll be reasonable, but not before like the holidays or anything. But it'll be nice next semester if we go back in the classroom. It'll be I think it'll be a little bit easier to get a good routine going. So when I'm at home, everything's kind of haphazard. So not in the upcoming semester, no. Sometimes I do, or sometimes I teach pre-calculus, but what we teach does change from one semester to the next, even though there's certain classes that we always like to teach. Like I always teach some stats classes, I always teach a calculus level class. Um, Almost always teach algebra, though I don't even need algebra classes in the spring, which is ridiculous because it's been. I don't know if I've ever had a semester where I didn't teach an algebra class, but in the spring I'm teaching 3 sections of statistics, and then calculus 2, and then differential equations. So. I don't know if I want to teach the same thing 3 times. I would actually prefer to have like an algebra class in there to mix up the day. But there's some benefit, at least in teaching the same 3 classes. So it's a little less work to prepare. So there's that aspect as well. Yeah, and I'm hoping y'all do enjoy the online class. I mean, we know it's not optimal for a lot of you, but like I know a lot of people would probably benefit more from being in person than being online, and because we're really missing a lot. We're able to interact some, like we are now, just through typing in questions or comments, and you know, interacting like that. It's a little bit different when you're able to say your question, and I can get a little more information. Like, it's a little bit easier to convey information just talking to someone versus typing something out. So I guess that's what I'm trying to say. But can't beat the commute. The commute from my bed to my computer. All right. We should probably get started, since I already talked about how short on time we are. Let's I think we'll start with section 6.3 today. which is on exponential functions. Now we're not going to have any more chapter exams. Originally I did want to have a 4th chapter exam, but that hasn't, there's really no chance of that occurring. So instead, we'll just cover 5 more sections in these 4 days, and then review, and then have a final exam. So, all right. There you go. So we look at exponential functions, the general form. General form is f of x equals b to the x, where b is a base number and x is our exponent, and it's a variable expression. Variable expression means it's, well, typically it'll be like a polynomial. You could have something a little more elaborate there, but generally that's what it's going to be for our purposes and our work that we'll do. So we could have something like f of x equals 2 to the x. We also have a special function called e to the x. Now, e to the x, this is called the natural exponential. And if you have when you look at geometry, we have pi, which is a significant value. In algebra, we have e, which is a significant value. E is approximately 2.71828, and it just keeps going the same way. Pi is 3.14159, etc. I only memorized like 5 or 6 decimal points. I don't know anything beyond that. And this number e actually shows up in a lot of different places in higher mathematics. When you get to calculus, when you get to differential equations and applications of physics and engineering, it ends up being a significant nut value. And so we introduce it here, or you might have seen it if you had like a high school pre-cal class, or Algebra 2 even. Anyway, it's called the natural exponential because it was basically naturally occurring the way that it was discovered. But anyway, we have 2 buttons on our calculator that we use for exponents. A little bit of a glare. Okay. We have in this calculator, I have y to the x. This is my exponent button on this calculator. Other calculators, you might see x. Well, I can show you. X raised to a unknown value, blank. That'll be the exponent that we fill in. On the graphing calculator, we have the caret button. And some other TI calculators besides graphing calculators will have that. And we use that to find the exponent of something raised to something else. So if we wanted to find 2 to the 4th power, Um, yes. I guess that would be fine. I know on iPhones, at least, when you open up your calculator, it looks like this, but if you turn it sideways, you get your scientific. So you have right here x to the y, and that would be, that was an 83. It's not as good as 84. X to the y would be our exponent button here. So now, the nice thing here is most of these are fine. I said 2 to the 4th power, which we know is 16. So we get 2, exponent button, 4, enter, or equal, and it gives us a value of 16. Same thing here. We have 2, press the exponent button, enter 4, and equals, it's 16. So, and we should be able to get that result in any calculator. The general exponentials are pretty similar as far as how they're calculated from one calculator to another. So we enter our 2, our exponent button, and then 4, and then equals. Now we could even do something like 3.1 raised to the 2.3 power. And that's the beauty of this, is that 2 to the 4th power we can figure out ourselves. That's 2 multiplied by itself 4 times. It's not that hard to calculate that. But something like this where there's decimals, we absolutely need our calculator to find that for us, because that's just not something we can do by hand. You know, Brock, with the lockdown browser, it prevents you from using other programs on your computer outside of the test that you're taking. I don't know about other stuff. Honestly, I have no experience with it, so I couldn't tell you, unfortunately. .1 to the 2.3. So we get 13.494. Most of the time when we're rounding these things, 13.494. Whenever we're rounding these things, 2 or 3 decimal places is usually fine. Yeah, if only we trusted our students. How nice would that be? But anyway, it's not my decision, unfortunately. Okay, 13.494, so we got that. And I just rounded to 3 decimal places here. If we wanted to round to 2, that would be fine. Unless we're specifically looking for like a certain level of accuracy, like so many decimal places after, then 2 or 3 is perfectly acceptable. Now, the other button that we have on our calculators is the one for e to the x. Okay, we have the e to the x button, which a lot of the time, like on standalone calculators like this, see e to the x right here on the second level of functions above ln. So I would press second and ln, and that brings up e raised to a power, and then enter in like 2, so it'll be e squared, and we can get that result. So if I wanted to do e squared, on this calculator, this is where it's going to be a little bit weird from one calculator to another. E squared, I would press second, and then on my calculator, Ln, and e to the x is above it. That's why I've pressed. Enter the 2, and then equals, or enter, whichever one your calculator has. Or, on other calculators, such as on my phone, this one I actually have to enter the 2 first, and then here's the e to the x button, which, get out of the glare. So I enter the 2 first, and then hit the e to the x button, and it gives me the same result, 7.389. Okay. My phone calculator is the only one that takes that different entry of my 3 calculators that I have here, or 4 counting my phone. So I like to demonstrate that one at least. So other calculators, you might have to enter the 2 first, and then hit your e to the x button. In some cases, it'll be second and ln e to the x. Other cases, you have a separate e to the x button, like on the calculator on my phone, like I showed you. So, the main thing that we should focus on, though, is learning to use the calculators that we plan to use on the exam. That's the important part. And, you know, for our exam, they're going to, one of the things they'll check when you have your proctored exam or whatever, they're going to make sure you're not using a graphing calculator. I think you'll have to hold up your calculator to the camera or something. You'll need to show your ID card to the camera. It's really kind of a pain, actually. So just to prove your identity. You know. All kinds of stuff going into that. But yeah, for the calculator, make sure you have like a good graphing calculator, or non-graphing calculator specifically, that you're comfortable using, and you've practiced on a bit, so you're good using it. So, and again, this is why, you know, we can't have, if we're not able to have class in person. I mean, normally if we're in a classroom, I have extra calculators I can provide, or we have a classroom set that floats around that we can use, and lend out calculators just for the duration of the test, and that's always nice to have. But anyway, all right. So that's the calculator process. Let's move on to the graphs of exponential functions. Now, much like some of our other topics that we've covered, alright, done with that side. When we look at the graph, we're going to establish the basic shape of the graph. See, I'm not sure about that either, Brock. That's I need to write these things down. Oh, thank you, August. I mean, if there's stuff I need to ask, let me know. Yeah, I would assume with the lockdown browser, it just locks you out of everything else on your computer. So that's what you have to expect to happen. You won't have access to your computer's calculator. Yeah, that's good. That's a good point. Anyway, with graphs of exponential functions, we establish what the basic shape is, what the basic concepts are, and then we can do transformations from there if we desire. Now, I'm going to use f of x equals 2 to the x. It's kind of a very generic exponential function that we can graph. And what I'm going to do is I'll make a t-chart here. Gosh. And so we want to plug each of these values into this function. Now, we start with a -2, and I wanted to point out what happens with negative exponents specifically. So at f of -2, we get 2 to the -2. You will have to take your own calculator, Amanda. Now, if you do it through the Math Lab, they may actually have one you can borrow from them. I don't know if I would proceed with that assumption, but it's better than going out and spending $20. Okay, so with our exponent 2 to the -2, this should have quite a bit. And what they'll probably do is they'll make sure the calculator is wiped down and clean before they give it to you, just for viral precautions. So, but yeah, calling them is a good option. Two to the -2. Anytime we have a negative exponent, what we do is that means we'll end up with 1 over 2 to the positive of that exponent. So essentially, we just take this expression, move it down into the denominator, and now it has a positive exponent. So 2 to the -2 is the same as 1 over 2 to the positive 2, which we then calculate as 1 over 4, or 0.25. Now, if you did that in your calculator, 2 raised to the -2 power, notice it gives us 0.25, which is the same thing as 1/4. So you don't have to do that by hand. You can just do it on your calculator and get the same result. Okay. Same thing with 2 to the -1. That's 1 over 2 to the first, or 1/2. So 1/2, or 0.5. What do you think 2 to the 0 is? I'll give you a hint. It's neither 2 nor 0. I don't know if that's as much a hint as it is a point of confusion. Anyone know what happens when you raise something to the 0 power? It's 1. Good. 2 to the 0 is 1. I actually went over why that was true in my I teach a support class for a business math course. Also, that's like my 6th class. Also, I'm looking forward to not teaching 21 hours in the spring. I'll just be back to my normal 17. So, anyway, it is 1 though, but the rule is anything raised to the 0 power is 1. There is an exception, but it's probably not worth getting into because it's really a calculus concept. But we'll just say anything to the 0 power is 1. Mm-hmm. In fact, if you're not entirely comfortable with that, the calculator will still help you out. It'll give us the same answer. Yeah, that's actually a good application there, Bach. That's like when you see something in scientific notation, for instance, it tells us the scale of the number, 10 to the n. Okay, ultimately the reason for this is complicated. What I did is I showed what happened when you have 2 to the point 1, the 2 to the 0.01, 2 to the 0.001, 2 to the negative 0.001, 2 to the negative 0.01, 2 to the negative 0.1. It showed it as progression, and that the only possible number that could be between these other numbers is 2 to the 0 is equal to 1. And that's kind of a tedious explanation, and I don't necessarily want to repeat that here. So it might just be easier to say for now anything to the 0 power is 1, although there is a very definite reason for that. It doesn't make any sense. I'm not going to lie. It doesn't make any sense that if we have 2 to the first power, it means we have 1 2. 2 to the second power means we have 2 2's multiplied together. 2 to the third power means we have 3 2's multiplied together. Why does 2 to the 0 not mean we have 0 2's multiplied together? And how is that equal to 1? That's really confusing if we start thinking about it that way. It just made it worse. But the reality is it is equal to 1, and we'll just go with that. No, actually. Technically, like, 2 as the exponent approaches negative infinity will equal 0 or approach 0, but that's the best we can hope for there. Yeah, technically an exponential function will never equal 0. Yeah. And we'll see on the graph exactly how that looks, which I should continue doing. 2 to the first power, that's just 2, and 2 squared, that's 4. Okay, so we got all our points there. Okay, so we get negative 2 comma 0.25, which we'll draw as best we can. negative 1 comma 0.5, 0 comma 1, 1 comma 2, and 2 comma 4. The reason I like to use 2 to a power, like 2 to the x, to demonstrate the general shape of the exponential is that the numbers are relatively small overall. Anything else, they get kind of out of control. Because what happens is, because the values grow exponentially, what happens here on this right hand side, we can see exponential growth means it's increasing at an increasing rate. Not only is it increasing as it's going up, but the distance from here to here is increasing as we go from here to here, or from here to the next one. Now on the left hand side, if I can manage to draw a proper graph, this is where I love my whiteboard, so I can erase my mistakes and draw it again. What looks like is happening here as it continues to the left. It's approaching 0. What kind of line do we have here? An asymptote, good. It's approaching 0, and the axis is actually the horizontal asymptote. So y equals 0 is the horizontal asymptote. Is that off the screen? It's a little bit off the screen. There you go. Just hiding it behind my picture there. Alright. When I first started teaching online in March, I didn't have a webcam, and I decided over the summer I needed to buy one because I think it was a little bit too impersonal. But everyone was dealing with a lot of stuff at the time, so I don't think it affected them too much, but I feel like it's easier to connect when you can at least see me talking to you, not just hear me, which I think was important. I just didn't have one at the time, and gosh, teaching supplies were, like for online teaching, very hard to get in the spring, so I was able to get this one this summer. I know, it would just feel so impersonal and alien almost, but it's like, who is this random person talking to me about math? It's nice to be able to see the person, I think. Alright. Plus it made me put in a little more work figuring out the software, which is good. Yeah, and I think it's easier to communicate for me to communicate to you and relay just relay information when you can see the person talking to you. There's some things you can convey via, I mean, probably can't see my face too well. This is honestly not the best web camera, but it's better than nothing, and at least you can see, like, I don't know if you'll be able to properly read my lips if you were a hearing impaired person, so, but yeah, the downside is that it'd be nice to virtually see all of you, like in I'd hate to have to buy another monitor. But that'd be cool, just for the interaction purpose. Actually talking to people versus talking to the camera. So, anyway, I do like, and this is. Yeah, I think you just don't have that connection, which is more important than is initially realized. I do have this. This is something our department gave us like years ago. It's just an old tablet, and I've never used it for anything. I don't know why they bought it for us, but it's come in handy. So you can see everything that y'all typed. I can see it on my screen to my right. It's actually a lot easier for me, though, not to turn to the right every 5 seconds and look to see if anyone said anything. It's actually a lot easier for me to keep tabs on everything. So that's just come in pretty handy, too. So oh, really? Yeah, it's like on my Twitch on my computer. I have the dark theme, so it's like a darker background, but everything's real white. The text is white. The names are still in color, which is neat, but the text is white. But I had to turn down the brightness a little bit on my tablet here, otherwise the battery would be drained after one lecture. I needed to make it through like 2 days, just for my own sanity's sake. But anyway, I don't know why I decided to use it all of a sudden, but it just realized I had this thing available I just wasn't doing anything with, and this would be perfect. So as much as we could, Brock, as much as we can. It is still a math class, but I enjoy it, and hope you all find it tolerable, at least. Usually, the first day after a test, I like it to be a little more easygoing. Especially like an online test. I know a lot of you were taking it last night. That's why I sent out the reminder, is that I looked at how many people had completed it, and I think it was less than half the class had completed the test when I sent out that announcement. It was like 5:30 or so, maybe 6 o'clock. So I know some of you are up late doing a math test. For me, that's another reason to take it easy today. But can't take it too easy because we have like goals and stuff, you know. All right, I'm going to call 0, 1 here the anchor point. And I call it the anchor point because that's the point that's going to be constant for any exponential function. So whether we have 2 to the x, whether we have 3 to the x, whether we have 4 to the x, 10 to the x, we're going to have this coordinate 0, 1. Okay? And again, that's because anything to the 0 power is going to equal 1. It doesn't matter what the base is. Any base raised to the 0 power will equal 1. So these numbers may change, and it may be that, if we look at 3 to the x, 3 to the x would look more like this. But also like this. So 3 to the x kind of does this rotation almost, but it has a different curvature to it than 2 to the x does. where it actually increases more rapidly and it gets closer to the axis more rapidly going to the left. And the same thing for 4 to the x. 4 to the x would start off up here, so it would go like very rapidly up. And then anything higher would continue to fit in between here. But all of these graphs would go through this anchor point 0, 1. What is the domain of these functions, do you think? Domain, remember, is our x values. So domain is how far to the left and how far to the right the graph goes. August, I believe you're talking about the range. Yeah, the domain would be negative infinity to infinity, or all real numbers. Yeah, and then the range, we would say it would be 0 to infinity, or y greater than 0. Yes. So horizontally, we know to the left it just keeps going. It's going to eventually get to 0, but that's at negative infinity, technically. And on the right, even though it looks like it increases very rapidly, it's still moving to the right. It still keeps going that direction. It just goes up a lot faster. So the domain will be negative infinity to infinity. It just continues infinitely to the left and to the right. Now the range, we know it goes up to infinity this direction, but as it kind of levels off going to the left, it never technically reaches 0, so we put a parenthesis there because we don't want to include 0. It just gets closer to, but not including 0. Okay, so it's important to note that we have a horizontal asymptote here at the axis at, I guess I should put that in parentheses, x-axis. But y equals 0 is the equation of that asymptote. And then we can find the domain and range from the picture. Now, with that in mind, and using that as our basic shape of exponential functions, we can find other graphs using transformations. So for instance, or for example, let's find the graph for 3 to the x minus 2 plus 4. Now, as far as sketching 3 to the x versus 2 to the x, you don't really have to show the different shape. We know it has the same general shape, but a little bit different curvature, like I said. But don't worry about that too much. We just want the basic exponential shape. We'll just shift it around to wherever it needs to go. Which directions are we going to have to shift this graph? Up 4. Good. To the left. To the right. Remember, if we have a minus here inside the function, this is technically inside the function because it's where the exponent is. Negative is to the right, positive is to the left. Yeah, we got away from it for a little while, and then it's coming back to bite us again. Now, Brock, you said something significant there, is that because our original anchor point is at 0, 1, it's the anchor point that's being moved up 4 and right 2. So we start from here, we go up 4 places, and then right 2 places. So 1, 2, 3, 4, up, 1, 2 to the right, and that's now the new anchor point for our graph. Okay. Now, because we're shifting everything up 4 units, where's the horizontal asymptote going to be? Well, originally, our horizontal asymptote is right here on the axis. But the asymptote would absolutely shift up with it. So it'll go 1, 2, 3, 4 places up like everything else. Anyway. And then our graph would not have changed shape. So we'll just draw it at this new location. Yeah, it does shift with it. Now technically when we move it to the right, that does a left or right shift does not affect the asymptote. Only the vertical shift will affect the location of the asymptote. So that's what to watch out for. We know our domain is still negative infinity to infinity, but what is the range? Five to infinity is close. 4. Yes. Notice that, okay, this is 5 right here, but the curve does go below 5 as it continues to the left. It gets closer and closer to 4, where the asymptote is, but never intersects. A good way to remember the range is always from the location of the asymptote and then up to infinity or down to negative infinity, whichever way it's going. Okay. I think I have room for a graph over here. do if a book wasn't in the way. There we go. Alright. F of x equals negative e to the x plus 3. Now the fact that this is e, don't worry about it too much. E, like we said, e is a number between 2 and 3, so the shape will be roughly the same as those two graphs. So we're not really going to do anything crazy here. What transformations are happening? This left by 3. What does the minus do again? Flip the graph over the x-axis, yes. So we start with our anchor point, which again begins at 0, 1. 1, 2, 3. We do call it reflection, yes. Reflection is a technical word, or informal word as we flip the graph down, which is, I think, a little bit shorter and more concisely conveys what's actually happening here. So our anchor point gets moved left 3. There's no vertical shift. But here's what happens. And this is where it's a little bit different working with reflections on exponentials instead of polynomials and things that we're looking at back in chapter 3. When we flip this down, that means, and again, flip the graph over the x-axis is a great way of putting this. This was, oh, sorry Amanda, this is our anchor point, 0, 1. This is where we always begin. So we go left from there to get to that location. Now when we flip the graph down, this point actually reflects to the other side of the axis. Okay. Now our asymptote is still in the same place. We've just moved the graph to where it goes the opposite direction now. This is one of the hardest things working with exponential functions, is that our reflections are no longer quite as straightforward. Okay? Because our anchor point is no longer at the origin like it was for every function we looked at in chapter 3. Our anchor point was at the origin. Because our anchor point is not on the origin or not on the x-axis even, when we do that reflection, it flips across the axis, and that one's a little bit challenging to remember. Any questions there? Correct. Always start at 0, 1 for exponential functions. And then next section, we'll look at a function that has a different anchor point. So it's going to be a little more to remember this time. domain is still negative infinity to infinity. Oops. Our range. Now our range, because the graph goes down to negative infinity, we'll put that first, and then it's still getting closer and closer to 0. So negative infinity to 0 for the range. Or y is less than 0 in this case. If we look at where the graph would have been before we flipped it, I don't know if that makes it any easier. It's like we're taking the whole paper and folding it down across that axis. Okay. Yeah, a mirror would be great in this situation. I don't have anything close to that here. Now, the last topic we look at today is solving exponential equations. And the general principle we apply is that if b to the x equals b to the y, then x is equal to y. Now, basically what it says is if we have the same base on both sides, if these bases are equal, then the exponents have to be equal to each other. Now, in some examples, it's really obvious. If we have 2 to the x equals 2 to the 4th, then clearly x has to equal 4 for these to be equal to each other. Now you can think of it as canceling out the base, although we're not exactly doing that, but essentially we're doing that. So that might be a good way to perceive this. Okay. If we instead said, for example, 4 to the x equals 64, what we would do is say, okay, we know the left-hand side has a base 4. Can we write the right-hand side as a base 4? Like, is there some power that 64 could be raised, or that 4 could be raised to equal 64? Does anyone know what the power is? Three. Good. And then our conclusion is x equals 3, because we just get rid of the basis, so it's x and 3. This is probably one of the easier aspects, I hope, from working with exponential equations. One where it's a little bit more strange. Let me show you this example. And it's not that we're just always going to have x here. We may have like 2x plus 1, x minus 4. We'll have some different binomial or linear terms. You sometimes even maybe a quadratic term there. It just depends on the function. let me do another simple one, but with the an answer like that. So if we have 2x plus 2 to the 2x plus 1 equals 8, first thing we do is figure out 2 to what power equals 8. That would be 2 to the third. We get rid of the 2's and we still have an equation to solve. So we would set 2x plus 1 equal to that 3. So whatever is in the exponent on the left-hand side is equal to the exponent on the right-hand side. So then we just have to solve this linear equation, subtract the 1 from both sides, so 2x is equal to 2, and then divide by 2. X is 1. Okay. One more of these, and I think we'll be good. Let's see. We have 9. The 2x plus 1 equals 27 to the x minus 3. In this case, we see that 27 is not a power of 9. 27 is a multiple of 9, but being a multiple of a number is not the same thing as being the power of the number. Being a power of the number means we can raise one number to an exponent to equal the other. And unfortunately, that's not true here. But even though 9 and 27 is not a power of 9, or vice versa, is there some other number that we might be able to use in this case? Is there a base that might be common to both numbers, 9 and 27, that we could use? Exactly. 9 is 3 squared and 27 is 3 cubed, so even though we can't make 27 a power of 9, we can make both of these numbers powers of 3. Okay. So at this point, we have to figure out how to deal with these different exponents. We have 3 squared raised to the 2x plus 1. How does the 2 and the 2x plus 1 interact? Well, when we have a single base raised to a power raised to another power, let me write the rule down over here. If we have 3 to the x times 3 to the y, if there's two separate terms multiplied together, we add their exponents. But if we have a single base 3 raised to an x and then raised to a y, in this case we multiply their exponents. So we'll need to multiply 2 times 2x plus 1 and 3 times x minus 3. Now essentially that means we'll distribute the 2 and distribute the 3. So that gives us 4x plus 2 and then 3x minus 9. At this point, because we now have the same base, we can get rid of our 3's and just say 4x plus 2 equals 3x minus 9. We'll subtract the 3x from both sides. So x plus 2 equals minus 9. And our last step will just be to subtract the 2. So x will equal negative 11. And that's our solution there. Now, there's other exponential problems we'll eventually look at in section 6, but they require us to get through section 4 first, because once we get through section 4, that's going to open up a lot more possibilities for us. So we're going to leave it at that for today. Let me give you a few problems to look at. This is page 446. Look at 1725. 45, 47. 53. 59. Then I don't like some of these. 71 will be good. 73. 75 and 77. There you go. So, go ahead and take a look at those. That takes care of section 6.3. The applications here are pretty straightforward. Basically, the idea is just plug in the value and get the result. But yeah, we won't worry about that in the interest of time. So we'll stop there, and you all have a good rest of the day. And hopefully, by the time Monday comes around, I'll have your test graded. Yes, 45, 47, 53, and 59 are graphing. First two are just using the calculator, and the last four are solving equations. So it's a little bit of everything that we did today. Yeah. So have a good weekend, y'all, and I'll have your test graded by Monday. I really hope I do, because I don't need more stuff to do next week. But yeah, y'all take care, and I'll see you then. Bye.